Hello, and welcome to College Physics 2, Lecture 14, Circuits and Kirchhoff's Laws. I just wanted to mention real quick that if you are a long-term viewer of my channel, you will recognize that it has been a long time since I have uploaded any videos. My goal here is to re-record 3 lectures, lectures 14, 15, and 16 of my College Physics 2 course because they are lost to time. In a way, that could be a good thing because I feel I have made these lectures much better since the first time I went through and recorded everything, so I hope you find these useful. Now, we're going to just jump right into the middle of things as if we have been going through all the lectures in order, so I am approaching these lectures with the basic understanding that you have a basic understanding of this material going forward. Let's start with a question. Right off the bat. Question 14.1. You're given a picture of a light bulb and a battery, and it asks, does this bulb light up? Well, no, it won't. In this case, sure, it is a light bulb. It should light up. It is connected to a battery, which we often think of as a power source, but there's no complete path for charge to flow. So it's connected to the positive terminal of the battery right here, which is great. But without a path for current to flow, in other words, a full loop, you don't get any current. So as a result, there's no current that's flowing through the bulb, and thus it does not light up. You need a potential difference for this to occur. Right now it's only at the 3-volt positive terminal of the battery. Anyways, this kind of is a segue into the deeper discussion that we need to have. So one of the first things we need to be able to do when dealing with circuits is understand what you're looking at, or to be able to draw a circuit yourself. So to get us started, we just need to make sure that we get familiar with the various circuit elements that we will encounter in our course. I want to be clear, there are certainly other circuit elements that might be involved in the real world, like inductors or LEDs or logic gates, everything like this, but right now we're focused on the basics. So for our purposes, we're going to deal with batteries, resistors, light bulbs, capacitors, and occasionally a switch or two. So what you're seeing is, in the top, you're looking at a physical representation of what the object might look like in the real world. However, on the bottom half of this diagram, you're looking at what we call the circuit symbols or schematics of what you would draw in a circuit or see drawn in a circuit diagram. Now, all of these are pretty straightforward. A resistor is given by a bunch of scribbles. How many scribbles you give it does not matter. It's just a jagged scribble to represent a resistance. A light bulb quite literally looks like a light bulb. Big surprise. A capacitor, which we know is made of 2 parallel plates, is shown as 2 parallel 2-dimensional plates. And a switch, quite literally, looks like a little arm that swings to open and close the switch. So the point is, all of these are really straightforward circuit diagrams, or symbols. But it is also helpful that when you draw these things into your diagrams that you label them. So for example, if you have a resistor of some resistance, label it with that resistance. A capacitor with maybe some capacitance, label it C for the capacitance. And if you have a battery of some potential difference, some voltage, label it with whatever that voltage is, V. All right, that helps you be more familiar with whatever is in your circuit. I wanted to make a quick note about batteries. Here you're seeing a battery represented as 2 sets of parallel lines. On the top you have a long line, then a slightly shorter line, then another longer one, then another shorter one. What you're seeing here is a representation of how many cells the battery has, which for our purposes in my class does not matter. We don't look at how many cells a battery has. You might see me or other people also draw a battery with just 2 sets of parallel lines, one long, one short. Either way, it's representing a battery. One thing that I personally always encourage is adding a plus sign on the positive end of the battery, which, if you look at the picture, is on the top here. The side with the longer line is the positive side of the battery. So that's our positive terminal. So whichever side has the longer line is your positive terminal, and then it's just implied that the other one is your negative terminal. Okay, while we're here, let's add in a little joke before we move forward. So here is Thor representing a bunch of our different circuit symbols. Okay, so again, our goal is to understand what we're looking at when we see a circuit diagram. Here is a picture of a circuit, right? This is maybe a relatively realistic, three-dimensional, real-life view of a circuit, in which you have a resistor on the left, to be clear, a battery in the middle, and a capacitor on the right. How would you represent this as a circuit diagram, using those symbols that we just introduced? Well, remember that a resistor is a scribble. That's how I refer to it. It's the scientific term. A battery is those sets of parallel lines, one longer than the other. And a capacitor is just two perfectly parallel plates. So you would just use those three circuit symbols in your diagram. Now, one other thing to mention before I show you what it looks like. We tend to simplify things as much as possible. And what that means is drawing our wires as straight lines. It's more complicated and sometimes even confusing if you draw these arcing paths that the wires are taking. So let's simplify it and make it straight lines with corners. In other words, we might see something like the following circuit diagram. Now, I purposely show you this diagram for a reason. Right off the bat, after a couple seconds of students looking at this, I would assume they have questions. First of all, the battery's in the middle, but we just drew the battery over on the left-hand side, basically swapping its position with the resistor. That might be a question to someone who's new to this. Additionally, the way the wires are connected is a little bit different. So I just want to go through and explain what we're doing here. First of all, notice the straight line connections. We're using straight wires everywhere around the diagram, using corners to show the bends and things like that. So again, we always try to draw kind of a boxy or squared version of the diagram, or of the circuit. Second, it's not necessary, but the way I view it is it's most useful, I would say, in my opinion, to usually, if you can, draw your battery on the left-hand side. You don't have to. You could put the battery back in the middle. That's totally fine. It wouldn't be wrong if you swapped the two positions here. But personally, I always like to draw the battery on the left-hand side if there's a single battery. Beyond that, the big question is, well, how do the wires make sense here? Because here we're seeing a single wire coming out of the battery and going straight to the resistor, and then a separate wire going from the resistor to the capacitor. Well, here we're seeing it as one single wire in a way, right? We have the negative terminal of the battery as a single wire going to the resistor, just like we have above, but it's a straight line connection over to the capacitor, whereas in the picture above, it's two completely separate wires. That's okay. Why is that okay? Well, keep in mind that we use the concept of ideal wires. Ideal wires mean that there's no voltage drop across our wires because we're assuming there's no internal resistance in those wires. We do that because, I mean, yes, in the real world, there is going to be some resistance, right? They have to flow through the metal. But the resistance in a wire is often so much less than the resistance in any other circuit element, like a resistor, for example, that it's negligible. So the point is, our voltage stays the same everywhere along our wires. So let's just say we have the 0 volts on the negative terminal of this battery. Who knows, maybe it's a 9-volt battery. At the negative terminal here, maybe I should use blue for negative. At the negative terminal, it's 0 volts. That's our 0 point. So what that means is, if we're using the idea of ideal wires, everywhere along this connection is going to be 0 volts. Because they're ideal wires. Any one point is 0 volts, they're all 0 volts. So that means it's 0 volts at the bottom of the resistor, 0 volts at the bottom of the capacitor, and so on. Right? I can even label that. So what we're getting at here is that it's all the same potential. It's all the same. So up here in the picture, the same thing applies. If this is 0 volts, then everywhere along this wire is 0 volts. So everything along this wire is 0 volts as well. So there's no fundamental difference. We try to simplify things as much as possible. Why draw two separate wires if you can just make it one that splits? Again, You are welcome to draw two separate wires. You wouldn't be wrong in doing that. But we try to simplify things as much as possible. Now, the top side of the battery is much more straightforward. So if you were able to make sense of the bottom side, great, because then the top's a lot easier. The positive terminal of the battery, which would be 9 volts in this example, is directly connected to the top of the resistor. So here we have it, directly connected to the top of the resistor. And it's also directly connected to the top of our capacitor. Well, just like we see over here. So everything is the same in these pictures. Now, I've done a lot of scribbling, of course, on this picture, but hopefully that kind of pieces things together for you. It's really one of those trial and error parts of physics where getting used to drawing these diagrams takes time. You're not going to get it every single time right off the bat. It's a guarantee, right? You have to just practice and practice. See more diagrams, make more diagrams. You'll get the hang of it, I promise. To practice, while we're at it, let's do 2 questions together. On the right, you're given a picture of a circuit. There's a battery on the top, a resistor on the left, and 2 capacitors. Which of those circuit diagrams matches the circuit shown? So take a moment to think about it, and then we'll talk. Okay, well, let's just follow the wires. I can't encourage you enough to just literally trace out the paths. Here, we have the positive terminal of the battery. We don't know what the number is, that's irrelevant. That positive side of the battery is connected straight to the top ends of 2 capacitors. So let's look at our diagrams. Here, positive terminal of the battery is connected straight to the top ends of 2 capacitors. Hey, so far so good. In B, the positive terminal of the battery is going straight into a resistor. That is not what is shown in our circuit. It shows the positive end going to 2 capacitors. This is not correct. In fact, in C, it's the same situation. We have the positive terminal of the battery. Yeah, it's being connected to 1 resistor there, but it's also being connected straight to a resistor. Again, that is not the case. So we already narrowed it down to knowing that A must be the answer, but let's just check the rest of the circuit to make sure. It also shows the negative terminal of the battery, which I'm using blue for, directly connected to one end of the resistor. Let's check. The negative terminal of the battery directly connected to one end of the resistor. Good, excellent. Now that resistor is then connected to the 2 capacitors. And we indeed see that here. The resistor is connected directly to the capacitors. These 2 pictures are the same thing. So that's my process and how I figure out if the diagrams make sense. I actually color code it when I'm doing this myself just to make sure, right? I use reds for positive sides, blues for negative sides, and it helps me piece together which one is correct. So with this in mind, try one more example. You have a picture of a circuit on the right. Again, see which one of the circuit diagrams matches that circuit. Okay, well, in this case, it looks a lot more confusing, right? Because we have even more capacitors, there's weird things going on here. But again, if you color code it, hopefully, it should make sense. So let's start at our positive terminal. The positive terminal of the battery is connected directly to a 75 ohm resistor. Let's check. The positive end of our battery is connected directly to a 75 ohm resistor. The positive end of the battery is directly connected to a 75 ohm resistor. Be careful on this one. Our battery is upside down. This one shows the positive terminal on the bottom connected to a 100 ohm resistor. Not correct. And this one here, the positive terminal is connected to a 50 ohm resistor. Not correct. The positive end of the terminal of the battery is also connected to a 50 ohm resistor. Well, looking at B here, it only shows a connection to the 75 ohm resistor. So once again, we have found our answer without even looking at the other half of the circuit. The answer is A. we see the positive end of the battery connected both to a 75 and a 50 ohm resistor. But let's check everything else like we did in the last one just to make sure. The negative terminal of the battery is connected both to the 100 ohm resistor and to the 75. Negative terminal connected to the 100 and the 75. Excellent, that's what we want. And then that 100 ohm resistor is connected to the 50. And indeed, we see that here. That is the correct circuit diagram for the circuit on the right. Now again, you are seeing the battery shown on the left side rather than in the middle. Don't let that confuse you. Again, it's pretty standard to represent your batteries on the left sides of these circuits. Again, there's nothing wrong with drawing it in the middle of your diagram if you want to, but it's just one of those standardized things that we do. Again, if you just follow your connections using reds and blues as I do, you'll be able to make sense of the right diagram. Okay. Well, hopefully with that out of the way, we can now start to reintroduce some laws and apply them to circuits that show these circuit diagrams now, and you'll understand it. So, this lecture is partially referred to as Kirchhoff's laws. We have previously in my lectures already talked about one of these laws, which is Kirchhoff's junction law. Again, Kirchhoff's junction law states that due to the conservation of mass, and thus the conservation of charge, because charges have mass, the total current that enters a junction, so a junction again is a split or branching path in a wire, the total current that comes into a junction has to equal the total current leaving that junction. So I'm using blue to show entering, red to show leaving. The way I say this is what comes in must go out. Charge is conserved. Just because the wire splits, charge doesn't just magically build up in this junction, or it doesn't magically leak out into space, right? Charge is just split. If it's equal resistances in each path, maybe if it's 1 amp coming in, you'd get 0.5 going out in each path for a total of 1. Or if you've got double the resistance in one path than the other, maybe it's 0.66 current in one and 0.33 in the other. The point is, no matter what's going on in your circuit, the law still states whatever comes in is equal to whatever goes out. Mathematically, we write that as the sum in equals the sum out. Again, where capital sigma represents the sum of in math. So for the picture on the right, you can see the equation applied. Current 1 is coming in. That has to equal the total current going out, 2 plus 3. What comes in must equal what goes out. Pretty simple, I think, overall. You can, of course, make this complicated if you have some really bizarre, complex circuit. But again, if you take it one junction at a time, it's very straightforward. So, let's practice with a question real quick. The diagram below shows a segment of a circuit. What is the current in the 200 ohm resistor? In other words, right here, I equals what? Okay. Well, first of all, this one can be somewhat confusing to students when they're new to this because it tries to trick you, as if physics wasn't hard enough as it is, right? It mentions this is a 200 ohm resistor, but that is completely irrelevant. This number does not matter for this question. I'm just trying to erase it here with my white pen. All right, it doesn't matter, right? Because all we're focused on is the current right now. We see a current of 2.5 amps coming into this junction, where we see a current of 1.5 leaving that junction. So think about the difference. There's 2.5 in, 1.5 out, right? So just find the difference. Hopefully, you can do this mental math, right? 2.5 in, 1.5 out means we're having a missing 1 amp, which is B, in that resistor on the right-hand side, right? For a total of 2.5 amps. Okay, so not too bad, right? Conservation of current, in other words, Kirchhoff's junction law, is fairly straightforward for what it's worth. We do apply it to much more complicated things later on, but one step at a time. So this was Kirchhoff's junction law. But he has more than one law. And the next one is a little bit more complex, and it's also used a lot. Well, both of them are, but so we're going to spend a little bit more time looking at the next law and do a much bigger example in just a moment. So, to get us started with Kirchhoff's loop law, think about the circuit that you see on the right, which consists of a battery and two resistors connected by ideal wires. Think about what's happening to charges that move around in this circuit. Okay, so first of all, again, I'm coming into this lecture with the assumption you have a basic understanding of the things we've talked about in my prior lectures. So at the negative terminal of a battery, we say it's 0 volts. That's our 0 point. We always start there as our reference point. Then, who knows how big the battery is. I like to refer to 9 volts as a standard. So let's say it's a 9 volt battery. Okay. Well, if that's a 9 volt battery, that means the positive terminal, or point B in this case, would be 9 volts. So, and to be clear, the 9 volts here is the EMF of the battery, or the potential difference established by the battery. So, starting at point A, think about what happens to our charges. As you move up through the battery, how can I draw this? Maybe I'll use purple. As I move up through the battery, remember what batteries do. We, in this book that I use in my lectures, refer to them, that is batteries, as charge escalators. In other words, they take your charges and lift them up to higher potential, in this case from 0 to 9 volts. So we have a greater potential at the top. So you see that on this little graph here. As you move through the circuit, you're starting at point A, and as you move up through the battery, the charges are brought up to a higher potential at point B, which in this case I've decided is 9 volts. Okay? Well, then you move through the wire to point C. We use the concept of ideal wires. Remember, that means there's no loss of potential when you move through them. So you see that on this graph is just a horizontal line, because the potential didn't drop or go up at all. It stayed the same as we move through the wire. We then hit resistor 1. Well, keep in mind what resistors do. Resistors decrease our potential. We call them voltage drops. So, as you move through that resistor, it's going to drop your potential. As I move from C to D, we're going to see a decrease in our potential. Now, in this case, because we're going to assume they're identical resistors, and there's only 2 of them in the circuit, we would assume then if they're identical resistors, they would drop the potential by half of the total. So if it's a 9 volt potential supplied, these would drop your potential by 4.5 volts. So that's what you see in our graph. We see our potential coming down by 4.5 volts. So this little point here is 4.5 at point D. Then you hit resistor 2. Again, assuming they're identical resistors, you would see an equal drop in potential by 4.5. So in our graph, we see us again go down by 4.5 volts until we hit point E. And notice where we're at point E. We're back at 0. That's a good thing, because we are now going to move along an ideal wire where it stays 0, and we get back to the negative terminal of the battery, the starting point, which is always defined as our 0 potential point. So we're back at 0, and now basically the whole thing repeats, and you start over again. So this is what happens in our battery, or in our circuit with a battery and 2 resistors. So okay, great. Then you might be asking, well, okay, what does this have to do with anything? Why is this important? What is this loop law? Well, the loop law summarizes what I just laid out. Notice that we started at 0 volts at the negative terminal of the battery, and when we got back there, we ended up at 0 again. What this is telling us is that, in a way, this is by conservation of energy, we're back at the same potential, so the total potential around a loop is equal to 0. This is true for any loop, no matter how big it is, no matter how many things are in it, no matter what things are in that loop. If it's a loop, the carrying current, you're going to see a potential difference in total around the loop of 0. Always. That's why it's a law. It applies to every loop. So that's what this equation is saying. The total potential difference around a loop, in other words, the sum of all individual potential differences, is equal to 0. Yes, individual elements have a potential difference, right? To be clear again, in this picture, the battery gave us 9 volts. It has a potential difference. But the total all the way around the loop is 0, because the resistors then drop it by 9 volts and bring us back to 0. So I can't emphasize this last point enough, though. It applies to any loop. Later on in our lectures, you'll see what I mean by that. Now, this is a little bit more complicated than the junction law. So what I like to do is use analogies. Anytime things get complicated, if we have a way to describe it with an analogy of something that makes more sense, we should do that. So I made this analogy. This photo, I'm using little pictures from my textbook, but I've completely changed the picture and rewrote all the things on it. So I've kind of adapted it to give you something new. Think of this in terms of gravitational potential energy. It's hard to imagine electric energy and potential energy and voltage and all these things because we can't actually see the charges. We can't actually see them moving up in the battery and down in the resistors. So think of this in terms of gravitational potential energy. Let's go through the circuit one more time. Bear with me. I think this is important. At least as someone who is a visual learner, I love analogies. Let's start at the, oops, I meant to use blue, at the negative terminal of our battery, the 0 point. In our analogy, that's point A. I've labeled the points here in this diagram as well. You're at the 0 point, 0 height. You're at ground level, right? The battery then takes you up to a higher potential at point B. I'll make that red. Okay, so it brings you up to a higher potential. Well, as you walk up a hill, you are bringing yourself up to a higher gravitational potential energy at point B. So in a way, these are analogous. You walking up a hill is you giving yourself gravitational potential energy. A charge moving up through a battery is it giving itself electric potential energy. Okay, great. Well, now, from point B to point C, we are moving along an ideal wire. Again, that means that there's no change in your potential. So that means, in this picture, we're just moving from B to C, horizontally. There's no change in our height in this example. Right? No change in height or no change in potential in our circuit discussion. Well, we then go down through the first resistor. That brings us down to a lower potential. So that's the same as us walking down to a lower height at point D. Okay. Well, we then, I'll switch to blue here, move down again through another resistor to point E. So we walk down another hill to point E. We've lost potential or lost height in this analogy. Well, again, notice where we are. We're at 0. Just like where we started. We then can start over. So maybe you walk around and come back to the start and do this over and over again, right? So again, for me personally, I love analogies. I'm a big visual learner. I think it's helpful to see things in context with these analogies. The one thing I just want to emphasize, when we're talking about gravitational potential energy, remember, I've said this before, height plays the same role as potential. So in these analogies, height plays the same role as potential. Higher height in gravitational potential energy means higher potential with electric potential energy. These analogies are so useful to someone like me who's a visual learner, and I think really most people are visual learners. So Being able to relate what's going on in our circuit to something we can visually imagine in the real world, I think is incredibly beneficial. Or if you're not a visual learner, you didn't like the analogy, then just pretend I didn't say anything for the last 3 minutes, right? But hopefully you find that useful. Okay, well, I have one more thing to introduce to you before we do an example. This loop law is very useful, but in order to get to 0, we have to have pluses and minuses, right? Because, maybe the battery gives us a positive 9 volts, then these guys have to subtract us by a total of 9 volts. So we need to make sure we understand when to apply positive signs and when to apply negative signs. So let me just step you through the signs of potential difference when dealing with these circuits. First of all, in pretty much every case, that's why I put a yellow asterisk here, in most cases, whenever you move across a resistor, you're going to have a voltage drop. Because it's a decrease, we see a negative sign for the potential difference across a resistor. And the equation we use to represent that potential difference is just Ohm's law. Right? So Ohm's law is delta V equals IR. Again, in this case, we're just applying a minus sign because we know it's going to drop our voltage, just like we saw in that last slide. Right? We saw that minus 4.5 volts across our resistors. So the equation for potential across a resistor is just given by Ohm's law, and it's negative because it drops our potential. To be clear, I put an asterisk here because there are situations where it would be considered positive. We, in my course, will likely not encounter that kind of situation, but it can happen in more complex circuits, something called like a Wheatstone bridge, for example. In my physics labs, I believe you actually do build a Wheatstone bridge once, momentarily. But beyond that, you'll always think of voltage as a negative IR. So if for whatever reason, if you have a complicated, weird circuit and you are forced to go the opposite way through the resistor, then you would consider it as a positive I times R. But for my purposes in these lectures, that's not going to ever be the case. So for now, for our purposes, just think of it as always minus IR. Okay? Oh, remember there's an asterisk there if you move on beyond this course in physics. Okay, well, we also saw that if you move up a battery, in other words, up the charge escalator of the battery, we see an increase in potential difference. That's your charge moving up the charge escalator to a higher potential. In other words, like from this battery, from 0 up to 9 volts. So we see a positive plus sign here in our potential for that of a regular battery, where the potential difference, delta V, is just represented by the EMF of the battery, or epsilon. And again, I know it's annoying or confusing, but epsilon is literally a potential difference. It's just what we call the potential difference of a battery. We call it the EMF, or epsilon. Okay, but there is something weird with our batteries, sort of similar to what I mentioned earlier with the resistor. It is possible to go backwards through a battery. You'll see this in the example we're about to do. But if your circuit has 2 batteries and for whatever reason they're facing each other, in other words, positive terminals toward one another, for example, if one of the batteries is stronger than the other, it's going to force the direction of current backwards through the other battery. If that's ever the case, you will see a negative sign for current that is forced backwards through a battery. So be careful. There are situations where it can be negative. And again, you will see an example of that in just a moment. So practice, right? And then last but not least, I don't even have a picture for them because we aren't going to talk about them in this lecture. But if you're dealing with capacitors in your circuits, we have an equation from the past. The potential difference across a capacitor is the charge on the plates Q divided by the capacitance of the plates, C. It's positive, just like for a battery, if you're going through it normally from the negative to positive terminal, quote unquote, or electrode in this case, and vice versa. If you're forced to move from the positive terminal to the negative terminal, or positive electrode to negative electrode, or positive plate to the negative plate, then it would be a negative sign. But for now, we're not going to worry about our capacitors because we won't deal with them for 2 more lectures. So overall, these are your rules for plus or minus signs with potential difference. So let's put it all together now. Let's combine everything we've learned and try to break down one of these circuits and learn a little bit about it. Generally speaking, if you aren't presented with a circuit diagram, you're just being described a circuit, it would probably be helpful to draw it. That being said, you're almost always given a circuit diagram, so you're very rarely going to be drawing them yourselves unless you're in a lab environment where you're literally constructing a circuit in the real world and then need to represent it on paper. So for most cases in our lectures and problems that I give, you won't have to be drawing them yourself. Step 2. Determine the direction of current. In this example of the picture on the right, we know the direction of the current simply by this picture that's given, the circuit diagram that's given. We know that current is going to flow up the charge escalator, which means current in this circuit is then going to be driven in a clockwise direction due to that battery. So that's one thing I always encourage right off the bat. If you've got a loop, draw in the direction of your current in your circuit. You don't have to draw it as large as I did. I'm just doing that for emphasis. But we know we're going to have a clockwise current in this circuit due to the orientation of our battery. Then, determine the potential difference for each element and write out your loop law equation. In this case, the loop law equation, we have the potential difference of the battery plus the potential difference of the resistor, but that potential difference is negative because it causes a drop. So if you wanted to write out your full loop law, add the two things together, the EMF of the battery and then the voltage drop across the resistor. By the loop law, that total potential difference, epsilon minus IR, must equal 0. And then, fundamentally this delta V loop is useless. It's just kind of a statement. So from this point, you can solve this equation for anything that you're missing. And by the way, if you look at this, this is epsilon equals IR. This is Ohm's law, right? It's literally Ohm's law. So we haven't really done anything new here. It's just writing it out for the specific circuit. Anyways, let's get into our final discussion of this lecture. An example. Let's take what we've learned and apply it to this circuit, which is a little bit more complex than the last couple we've seen. Here we have 2 batteries and 2 resistors. For the sake of clarity, let me go ahead and label things. Let's call the larger battery epsilon 1 and the smaller battery epsilon 2. Additionally, let's call the top resistor R1 and the bottom resistor R2, just for clarity. Now, we have an interesting situation taking place. We already have a circuit diagram drawn, so our next goal is to determine the direction of the current. This is important for things we will be working on in the future, so make sure you know your current direction. In this case, we have 2 batteries. It's the first time we're seeing this. And be careful. Look at the orientation of these batteries. The plus side is on the top for the left battery and also on the top for the right battery. What that means is these guys are actually trying to drive current in the same direction. This guy's trying to push charges upwards, and so is this guy on the right. But one of them is stronger than the other. It's going to win the fight. So our 9-volt battery on the right-hand side is the stronger battery. So it is going to force the current to flow around the circuit, in this case, in a counterclockwise direction, excuse me. The 9 volts is bigger than the 6 volts. It wins that little fight between the 2 batteries. Okay. Well, at this point, we set up our loop law equation. Remember that the total potential difference around a loop has to equal 0. You don't have to, but you should always start at the negative terminal of your strongest battery. In this case, that's the negative terminal of epsilon 1, as I've labeled it. So I'll even label this as start here. Okay, and then follow the current around the circuit. So we are moving up the charge escalator of epsilon 1. So that is going to be a positive potential difference, or EMF of the battery, right? It's lifting our charges up to a higher potential, so it is a positive value. We then follow the current through R1. Well, again, our resistors cause a drop in potential difference given by Ohm's law, I times R. So it's a negative sign because resistors drop your potential, and I times R because for resistors we represent their voltage with the Ohm's law, I times R. Okay, we then reach this second battery. Again, keep in mind, the bigger battery wins the fight, so we're actually forced to see current go downwards, backwards through the battery. What this means is we have minus epsilon 2, a decrease in potential across that battery because the charges are forced in the backwards direction through it. And then last but not least, we approach our final resistor, R2. It's another resistor, it's another drop in potential given by Ohm's law. The total of all of these potential differences by the loop law must equal 0. So we now have an equation that we can work with. Again, delta V loop is irrelevant, so you can kind of just ignore that. But delta V loop is not really important here. So now, let me just erase it. We have our loop law equation for this specific circuit. At this point, if you can do this, you're well on your way because it's just algebra from here on out. Now granted, a lot of people still struggle with math and algebra, that's okay. But you've done the challenging part, in my opinion. The setting up of the problem, the understanding of your circuit. All you have to do is figure out how to rearrange this equation to solve for the current, I, because that's what it's asking for, right? Well, I is in two places in this equation, which can freak people out, but if we get the i's on the same side of the equation and factor it out, we'll be fine. So, to rearrange this equation, what I would do is keep epsilons on one side of the equation, but add the resistor terms to the other side. We haven't done a lot of work here yet, but all I did, to be clear, is add the I terms over to the other side. Okay? So, with this, notice that we have kind of separated the two different types of terms here. On the right-hand side, I have I times R1 and I times R2. Well, keep in mind, if I is being multiplied into both things, you can factor that I out to a single I times the quantity R1 plus R2. Right? Just some basic algebra trickery here. This is great because now we have a single I that we can solve for. There's only one step of math left. It's I times this quantity R1 plus R2. So divide those resistances over. In other words, we're going to end up with a current equal to epsilon 1 minus epsilon 2 over the sum of the resistances. We know both EMFs, we know both resistances, so we can just plug in and solve. We're almost done. E1 or epsilon 1 is 9 volts, 9.0 volts. E2 is 6 volts. We divide this by the total resistance, which is 40 plus 20. So this is what? 3 divided by 60, so 0.05, I believe, if I remember correctly. 0.05 amps of current. Now, this does look like a really small number, but it is typical to get small values for currents in most situations because to give you context, a household outlet usually delivers about 1 amp of current. And keep in mind, a household outlet could kill you with that much current. So 1 amp is actually a pretty big number. So when we're talking about just little batteries like this, you would probably expect in most situations to have smaller currents than that. So that was part A. We figured out the current in this circuit. So let me erase all of the stuff that I've scribbled on the diagram. Okay. There is a part B to this question. It also asks us to figure out the potential difference across each resistor. Well, thankfully, this is actually pretty easy. Potential difference across a resistor, again, is given by Ohm's law. So this would just be I times R1. In other words, a current of 0.05 times a resistance of 40 ohms for the first resistor. So this would give you 2 volts. And then you do it again for the second resistor. In this case, it's the same current because it's a series circuit. And this one is 20 ohms. So you'd get 1 volt. Should probably label this as 2.0 and 1.0. Okay, so think about what's occurring here. You can kind of check your work. Remember, we, by the loop law, should have a total potential difference of 0. So we've got 9 volts minus 2 volts in this first resistor. Okay, so minus 2, that brings us to 7. Then minus 6 volts. So 9 minus 2 brings us to 7. Minus 6 brings us down to 1 remaining volt. So when we get here, we indeed drop by 1 more volt to get us back to 0 volts at the negative terminal. So you can kind of check your work, right? I don't know if me scribbling in a circle in red here is very helpful, but just think of checking your work whenever you're done. You know your total potential difference has to add up to 0 volts, and we do indeed see that with this circuit. So hopefully that made some sense to you. This is your very first example of the loop law being applied. If you don't fully understand it, I get it. It's the first time you've seen it. The good news is, or if you don't like it, the bad news is, we're going to see this a lot more in our coming lectures. You're going to be dealing with the loop and junction laws a lot going forward. So we'll get more practice soon. As always, guys, thank you so much for watching. I will see you guys in the next one. Take care. Have a great rest of your day. Thanks for watching.